So let's do some practice. Here's an old exam. This is the Math 166, also we call it Calculus 2, Exam 2 from fall 2022. What a classic, a wonderful exam. We're going to have 7 problems to work through. Woohoo! And so we should get into it. Of course, as we always do, we want to make sure we get our credit, so we put our name. We'll call it answers. And well, let's have some fun. Number 1. We're asked to evaluate the integral of log of x quantity squared dx. And now the first reaction is like, how do we integrate that? What's the right tool? And we look at it and say, well, it's not one of our basic formulas for integration. Of course not. This is advanced integration, right? So we say, okay, well, what's the right tool to use? Definitely not trig sub, definitely not, partial fractions, things like that. Say, well, log of x quantity squared looks hard to integrate, but it's easy to differentiate. And that's a clue. So when something is hard to integrate, but easy to differentiate, and in particular, whenever we see log x, we say, oh, let's try integration by parts. Now, one of the things is, you might look at this and say, well, wait a second. If we're doing integration by parts, we need 2 parts. I mean, right? We need something multiplying here. We don't have that, do we? Well, here's the cool thing. We can always, if we only have one thing, we actually have a secret hidden thing, which is called 1. And so we can always think of it something times 1. So if you have something that's easy to differentiate but hard to integrate, say, okay, we'll try this trick out. Integration by parts where we add a 1 there. Now the nice thing is that 1 is very easy to integrate. And so we say, okay, we have our 2 parts. Now remember, our underlying formula is we have the integral of u dv is uv minus the integral v du. So we need 2 pieces. One piece needs to be something which is easy to integrate. That's the dv. And one thing is something that's easy to differentiate. That's going to be the u. Well, okay, so we have our candidates. There's no question what's happening here. And we say, all right, well, if u is log of x quantity squared, then du, the derivative of that, well, chain rule, 2 comes down, natural log of x, and then times the derivative of natural log, which is 1 over x, and don't forget a dx. Now the integral of 1 dx is x. So applying our formula, we're going to have uv, so this will become x times natural log of x quantity squared minus integral v du. Now notice the x's cancel. Beautiful. It's like they wanted it to. I think they did. I think they did want it to. So we have 2 natural log of x dx. I say, all right, great. So now we've improved our situation, right? Previously, we wanted to integrate natural log of x squared. Now we're integrating natural log of x. So remember, these x's canceled out. Now, okay, well, how do we do that? Well, the first time we did it, it worked nice. So this is we'll do it again, right? It's a trick so nice, we'll do it twice. So we're going to think of it as, again, there's a times 1. And we'll go through this. There's a u, there's a dv. And so we run our process again. U is 2 over x dx. V is x. So we have what? X, natural log x squared. We don't forget that part. Minus, now, this next part is a really cool way to save points. A lot of people forget this, but that minus sign throws a lot of people off. So I recommend parentheses. Parentheses are like life-saving apparatuses. In fact, I would say point-saving apparatuses here. And what do we do? Well, okay, it's u, v. So 2 log x times x, 2x natural log x minus the integral v du. So 2 over x times x becomes 2 dx. All right, so we have x natural log x quantity squared minus 2x natural log x minus minus, right? That's where you need that parenthesis becomes plus. The integral of 2 is going to be 2x. And because we want all the points, plus c. And there we go. Life is good. So integration by parts. And yeah, we should expect to see. It's actually a really nice technique, and based off of course, product rule. And so mostly the question is, can you see the parts? And sometimes, remember, there's a hidden times 1. And sometimes you have to do it more than once. But other than that, no big surprises. Just keep going, and we'll be okay. All right, well, that was a nice warm-up problem, and let's move on. Number 2, find the integral cosine cubed of 2x tangent of 2x. Now, this is definitely trig integration. Not trig sub, just straight up trig integration. And so when it comes to trig integration, the key is trig identities, rewrite, make life good. Now, there's sort of 3 camps when it comes to trig integration. There's the sine cosine camp, there's the secant tangent camp, and if you have a really mean teacher, there's the cosecant cotangent camp. But you know, we don't have mean teachers here. So okay, so there's 2 different schools of thought. So we want everything in terms of secant or tangent, or everything in terms of sine and cosine. The reason I mention this is when you look at this problem, you say, well, wait a second, you've got a cosine and you have a tangent. So which camp should we be moving into? And I recommend, look, when in doubt, go to sine cosine. That's sort of the default camp to belong to. And so here we want to write everything in terms of sines and cosines. So all right, so that tells us where to go. Okay, so looking at this, we say, well, tangent, we know something about tangent. That's the same as sine over cosine. So there's a sine of 2x over a cosine 2x and a dx. All right, well, hey, there's some cosine, so we can combine those together. That's no big surprise. So that's cosine squared of 2x, sine of 2x, dx. And this is an ideal scenario. We have a single sine, and everything else is a cosine. That's perfect. It's just what we want. It's exactly the kind of thing we would like. So the reason I say that is when we look at this, we say, oh, that single sine that we see on the end, that's going to become here, we're going to think of this as our du. And what will happen is, well, we're going to say u equal the cosine. So if you have a single sine or a single cosine on the end, beautiful. Life is good. If you don't, well, you work on it and you use your trig identity. So this one didn't have too many trig identities, to be honest. It just seems the only trig identity is the fact knowing that tangent is sine over cosine. Not the most exciting trig identity, but they're all good, right? Okay, so let's be careful here. What is du, the derivative of cosine? All right, paying attention. Well, the derivative of cosine is negative sine. So there's going to be a negative there. Sine of 2x, and is that all? No. There's the chain rule, right? So derivative of the inside will bring out another 2 dx. Well, okay, so we see that sine 2x dx, so we could say, all right, sine of 2x dx is minus a half du. So, what do we have? Well, we have the following. We have a cosine squared becomes a u squared. And then that sine 2x dx becomes a minus a half and a du. And all right, well, life is good. Why? Well, minus half is a constant integral of u squared. So when you integrate u squared, you would have u cubed over 3 Don't forget, of course, plus c, because we don't want to lose any points. Minus a half times a third gives us minus a 6. U is cosine, so we get cosine cubed of 2x plus c, and done. That's it. Our final answer. Wow. Really? Yeah. It's not so bad, right? Don't be intimidated. We can do these. We're doing great. So let's keep it going. All right, what's next? Number 3. Find the integral 1 over the root 16 plus x squared dx. Okay. There's definitely a hint here about what we're supposed to be doing. And the fact that we see this square root on the inside involving something squared plus something squared, right? Say, okay, all right, this is trig substitution. And people oftentimes like trig substitution think of that, oh, that's a scary thing. It's not so bad, right? I mean, the thing is that trig substitution says, hey, let's use our Pythagorean identities that lets us write something squared plus something squared equals something squared. Like, what? Well, why? Well, essentially, we're removing the plus is our goal. So we can now have something easy to take a square root. That's the whole idea behind our trig substitution. Now, there's a couple of different forms. If we have an a squared minus a u squared, well, that says our right substitution would be the sine function. If we have u squared minus a squared, well, that's a secant substitution. But we don't have either of those. We have something squared plus number squared, u squared plus a squared. And that says we should be doing a tangent. So this is a trig substitution which involves the tangent function. All right, so we begin. Now here, this is 4 squared plus x squared. So here, our u is our x, our a is 4. So we are going to make the substitution u is equal to 4 tangent theta. All right, so let's go through what's going to happen here, and then we'll, plug it all in. And I said our u, which is silly of me, because our u is x. That's okay. We have the ability to update. It's easy to make small mistakes. Okay, what happens? Well, first off, dx, derivative of 4 tangent theta, derivative of tangent, is secant squared. All right, so that tells us how to handle the dx part. Now what about the square root? Well, the moral here is, again, the whole reason why we're doing this is because we're going to make that square root go away. If it didn't go away, we made bad choices. So x squared will become 16 tangent squared. And what does we know about that? Well, we can pull out the 16s. Square root of 16 is 4. Square root of 1 plus tangent squared. And now we pull out another trig identity, right? 1 plus tangent squared is secant squared. And so what we really have is that the square root becomes 4 secant theta. Beautiful. Okay, so we now have the integral of 1 over the square root 16 plus x squared dx is equal to, okay, the square root downstairs, that becomes 4 secant theta. Now, upstairs, the dx becomes 4 secant squared theta. So 4 secant squared theta. And you're probably looking at this and say, aha, the only thing that's left is the square. Oh, wait, no, that's not how cancellation works. The way cancellation works here is we can cancel off a single secant. And the 4's cancel as well. So we say, oh, that's the integral of secant theta. Okay, well, great. Well, how do we integrate secant? And the answer is, we've memorized it. It's one of our 10 basic integrals, right? There's 10 basic integrals that we just know by heart, and that's on our list. And so we know it by heart. And this is natural log secant theta plus tangent theta and plus c. Now, don't worry so much about absolute values versus non-absolute values. All right, now you might say, well, how do we get these values, secant and tangent? Well, notice a couple of things. We have this expression here that says, oh, hey, look, tangent of theta, that's equal to x over 4, right? So we can say, okay, so tangent of theta is x over 4. And now we say, well, wait, look at this long string of equals. We have the square root of 16 plus x squared dot, 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 is 4 secant theta. Oh, okay. So that tells us, wow, secant theta, we know what that is. It's equal to the square root of 16 plus x squared over 4. Perfect. And so we can replace both of these parts. So this is equal to the natural log of x over 4 plus the square root of 16 plus x squared over 4 and plus c. And we've got an answer. All right, I'm going to make 2 more comments here. Even though we have our answer, this is the right answer, I'm going to make another answer right now. And here's a question for you. I claim that this is also the same as the natural log of x plus the square root of 16 plus x squared plus c. Are those equal? Now, it doesn't feel that way, right? Because what's happening? Well, what's happening is we got rid of the over 4s. So how could we get rid of the over 4s? Well, it turns out there's a cool fact about natural logs. If we have division, it becomes subtraction. So really what you have is the natural log of x plus the square root of 16 plus x squared minus the natural log of 4 plus c. But c is a constant, and it can absorb other constants. It's like a sponge. It just says, I'm going to soak up all the constants. So it can soak up that natural log 4 term into the constant. So this is, if you were to plug into, say, a computer algebra system or a fancy calculator, you might get this answer and say, well, wait, is that the same? And they are the same. So that's comment number 1. Comment number 2 says, well, what if I didn't notice this up here for the secant? What would I need to do? And the answer is, well, you start with the x equals 4 tangent theta, and you draw a triangle. And so what's the triangle? Well, let's move this up a little bit here. You'd say, all right, come here. You draw a theta in one of the corners, and you remember that tangent's opposite over adjacent, x over 4. And then you use the Pythagorean theorem to fill in the missing side. And lo and behold, and not a coincidence, the missing side is the same thing that motivated our original substitution. Again, not a coincidence. That's what we'd expect to happen. And now we can say, okay, secant, well, how do you find secant? Well, that's the hypotenuse over adjacent. It's the flip cosine over. So that's how you get the square root of 16 plus x squared over 4. So that's an alternative way to find secant. All right, so there you go. Those are the 2 comments. I guess we can box this one too. This is, of course, these are both correct. And just a matter of which one you want. And you might say, well, which one should I put? And the answer is just the first one you find. That's the correct answer. Don't panic about, like, oh no, am I getting it just the exact way that they got it? Don't worry about that. The people who grade these are pretty smart. They've been doing calculus for a long time, and they know how to write things in different ways. So, all right, well, that was a fun one. I always like a trig substitution problem. And it's really good because it does a couple of things. It really tests you on your trig identities and manipulation, and of course, recovering at the end. How do you get things back into your original variable. So they're fun. Be ready. They're coming. It's going to be there. But for now, on to the next problem. Our fourth problem. Evaluate the integral x cubed plus x squared minus 10x minus 16 divided by x minus 1 squared minus 6 dx. Now this is what we call a rational function. So think of it as polynomial over polynomial, because that's what a rational function means. Polynomial upstairs, polynomial downstairs. And so when we have a rational function, there's a very set procedure we follow. And essentially, we might have to employ partial fractions, but the first thing you always check is look at the degrees. What's the degree upstairs? It's a cubic, degree 3. What's the degree downstairs? It's a quadratic, degree 2. Well, when we see a higher degree upstairs than there is downstairs, that means we have to first do long division. All right, so step number 1, we're going to be doing some long division. And on a side note, looking at this denominator, x minus 1 squared minus 6 is not a very pleasant thing to factor. It's going to have some really weird numbers. So let's hope that after long divisions, they were nice to us and something happens. Okay, so if we're going to do long divisions, the first thing is we should expand this denominator. So this is x squared minus 2x plus 1. Subtract 6, which is x squared minus 2x, and 1 minus 6 is minus 5. All right, now, how does long division work? Well, what we're going to do is we're going to take the denominator, x squared minus 2x minus 5, and divide that into the top, x cubed plus x squared minus 10x minus 16. And the good news is you always just think about what's happening with the highest power. So x squared, x cubed. What do I have to multiply x squared by to get x cubed? X. Say, okay, so that's x. Now, multiply this whole thing we're dividing by x. So that'd be x cubed, subtract 2x squared, subtract 5x, and we're going to subtract off. Okay, so that means we don't have to worry about the x cubes. That's been accounted for. X squared minus minus makes 3x squared, right, because it's x squared plus 2x squared. Minus 10x minus minus 5x, that's minus 5x, and minus 16. And now, okay, again, leading terms. X squared, 3x squared. What do we multiply by? 3. Okay, so plus 3. So 3x squared. Then there's minus 2x. Sorry, 2x times 3. I can multiply. You know, it's oftentimes you forget to multiply the whole thing through. See, mistakes happen, which is why you pay attention. And double check. And the nice thing is, you should expect things to work out nicely. So if things aren't working out nicely, it's like, let's go back and check. Subtract, the x squareds cancel, minus 5x minus minus 6x becomes x. Minus 16 minus minus 15 becomes 1. Okay. Oh, not plus 1, because it's minus 1. There we go. I can do math. Yeah, slowly, and sometimes I have to do it twice. All right, because negative 16, positive 15, we're negative 1. What does all of this mean? Well, all of this says that the real integral is this part right here, x plus 3, plus this part, which was left over, our remainder, x minus 1, over x squared minus 2x minus 5. And that's the real problem. Okay, so that's our step 1. Okay, so long division to rewrite. Now, what do we do next? Well, now we come to this term and say, okay, what do we need to do here? Now there's a couple of scenarios. There's things like we employ partial fractions to rewrite it, or something nice happens, and occasionally we even throw in some trig substitution depending upon the scenario. Now it is true that this does factor, but you should always sort of do a quick check and say, did they give us something nice? Notice the numerator, x minus 1, versus the derivative of the denominator. Because you should always check, okay, if I take the derivative of the downstairs, do I get the upstairs? And the derivative of the downstairs is 2x minus 2. Is that x minus 1? Well, almost. And in our case, close enough, right? Because off by a constant is close enough. So if we think about it here, so x minus 1, or x squared minus 2x minus 5, if we set u equal the denominator, x squared minus 2x minus 5, du would be 2x minus 2 dx, take the derivative, and then I say, oh, move the half across. So half du is x minus 1 dx. Well, we have an x minus 1 dx. So this really becomes the integral of, we have a half du, move the half to the outside, and then the x squared minus 2x minus 5 is a 1 over u. So a good rule of thumb is try a simple technique before you look for the hard techniques. And the simplest technique when it comes to integration is substitution. So you should always say, hey, is there a good substitution for me to make? And save yourself some work, because we like it when that happens. We like it when we can save ourselves some work. All right, so we now update our problem in progress. Say, hey, what do we have? Well, actually, we can just about write it down now. So the integral of x is a half x squared. The integral of 3 is 3x. And, well, we didn't finish this one, but of course, we know integral of 1 over u is log of u. And so this integral becomes a half log of u. Well, where u is x squared minus 2x minus 5. And of course, because we want all the points, plus c. And we're done. Good. They were nice to us. They set us up so that we could have something that at the end was not so bad. And you should think of your calculus professors as nice. You should be like, wow, our calculus professors, they love us. They gave us something that we can do. So if things are getting really messed up and convoluted, you should step back and say, wait a second, I know my calc professors, they love me, and they wouldn't give me something terrible. Let me check my work. Maybe there's something nice going on. All right, well that's, oh wow, number 4 is done. We're over halfway. We're doing great. Number 5, all right. Let R be the region in the first quadrant bounded by the curve y equals 1 over x squared plus 4x plus 3. The x-axis, the y-axis, and the line x equals 3. And this region is rotated about the line x equals 5. Find the volume of the resulting solid. Now, let's actually shade things in. Okay, so we have the x-axis is this part. The y-axis is here, x equals 3 is this part, and there's this curve. Okay, so this is our region, and you'll see this line here is our line, x equals 5. All right, so that's our problem. So just so we can visualize it a little bit better. Now, all right, what are we doing here? It's kind of an application problem, and let's think about how this application works. Now, because they gave us our expression as y as a function of x, our natural inclination is to integrate with respect to x, and so we're going to do that. We'll follow our natural inclination. It says that, okay, we should think of our slices looking like this, so that when we rotate, what we're going to see is we're going to see these little tiny shells. Okay, so this This is our shell method. All right, so how does shell method work? Well, all right, we have that the volume is you add up your pieces. So that's what the integration means. We're adding up our parts. And then we say, what happens with each shell? Well, we have 2 pi, and then we have the radius, our height. Let's see if I can spell height. And then we have our thickness. Okay, so when I talk about radius, that's this part here. This is our radius. Our height is this part here. And our thickness is that little tiny part there. Okay, so let's put it all together. So in our case, what we have is we're going from 0 to 3. So, okay, 0 up to 3. The 2 pi, yeah, nothing happens, good. The radius, well, we're spinning around 5. So how far is it from an arbitrary x to 5? And you say, well, you subtract, right? Is it x minus 5 or is it 5 minus x? Right, it's going to be 5 minus x, right? Because it's high minus low. The larger value subtract the smaller value, and when we think about it horizontally, to the right is high, to the left is low. So that's 5 minus x. What's the height? Well, that's 1 over x squared plus 4x plus 3. What's the thickness? Well, that's just the thickness for our little slice dx. All right, so we'll clean this up a little bit more. We have integral 0 to 3. 2 pi we'll just sort of put in front. And we have 5 minus x over x squared plus 4x plus 3. Okay. So now, what's the right technique here? Well, the 2 pi, we don't need to worry about, that's a constant. So it's, again, polynomial, rational function. We don't need to do long division like we did in an earlier problem, because you look at the degrees. Downstairs degree 2, upstairs degree 1, life is good. There's no shortcut, there's no like, u equals the bottom, d equals the top. No. But x squared plus 4x plus 3, that's actually kind of nice. And in particular, x squared plus 4x plus 3, this part factors. This becomes x plus 1, x plus 3, and so we say, aha, we see what's going on. We're going to say that this is going to be a partial fractions because we have our nice setup here. Good. All right, so time to do a little bit of work. We're going to take 5 minus x over x squared plus 4x plus 3, and we're going to write this as a over x plus 1 and b over x plus 3. Because x squared plus 4x plus 3 factors this x plus 1, x plus 3, and we have our form. Now, I will say, what we just did, I don't want to trivialize it. This is the step where a lot of people struggle with in partial fractions, which is, what's the right format for what the partial fractions should look like? Oftentimes, people are okay with the next things, which are just to say, oh, okay, work it out, solve for A and B, life is good, Bob's your uncle. But getting the form is super important. So it's okay to remind yourselves of what to do. Now, in this case, we're in luck. Our terms downstairs are what we call linear, just involve x to the 1, and there's no repeated terms, so that makes things a lot simpler. So, okay, so it's a over x plus 1, b over x plus 3. So it's okay to make sure you have that down. Now, at this stage, there's a couple ways to do it. I like to do clear the denominators and then make good choices. So when I say clear the denominators, we're going to multiply both sides by this expression, which is the same as x plus 1 over x plus 3. So what we really have is that 5 minus x is the same as a times x plus 3 and b times x plus 1. Now, on this side, just the denominator clears out. So that's why we end up with 5 minus x. Here, the x plus 1's cancel, so we're left with an x plus 3. On that part, the x plus 3's cancel, we're left with an x plus 1. Okay, so now, good choices. There's other ways to do it, but I like to make good choices. So what's a good choice? Well, let's choose -1. So a good choice is something which puts in zeros. 5 minus -1 is 6. And then -1 plus 3 is 2. So 6 equals 2a. That says a equals 3. How about -3? Right? So that will make that term go away. Because remember, so I didn't say it out loud, but -1 plus 1 is 0. 0b is 0. That's why we like 0. You know, it's not the greatest thing for your bank account, but it's wonderful for a math problem. 5 minus -3 is 8. 0a minus 3 plus 1 is minus 2b. All right, so that says what? b is minus 4. Okay, good, good. So now back to our problem. So this is sort of scratch work to help us figure out that, lo and behold, our problem is the integral 0 to 3. We have our 2 pi, and then this 5 minus x over x squared plus 4x plus 3 is a, which is 3 over x plus 1, plus b, which is minus 4 over x plus 3. Okay, so, well, these are things we can integrate. So let's integrate them. So, whoops. If we're going to integrate, we don't need the integral sign anymore. So we have the 2 pi, then we'll have 3 natural log x plus 1 minus 4 natural log x plus 3. Evaluate 0 to 3. Okay, well, we're almost there. Let's move our page up a little bit here. And, okay, what do we get? We get the following. This is equal to, okay, so we have a 2 pi out in front. Now, plug in 3. We'll have 3 natural log 3 plus 1 makes 4, and minus 4 natural log 3 plus 3 is 6. Okay, and all right, that's when we plug in 3, but don't forget we also have to plug in 0, so we subtract, and then we'll have 3 natural log 0 plus 1 is 1, and then minus 4 natural log of 0 plus 3, which is 3. All right, now in some sense we're done, but let's go ahead and clean things up, because it's nice for things to be clean. So, for instance, natural log of 1 is 0, and then, well, we have a minus, which makes a plus, so we can say this is 2 pi of 3 natural log of 4, and then we say, okay, there's a 4 and a 4. We can put those together, all right? So we can put 4 natural log 3, because minus makes plus, minus 4 natural log of 6. And if we remember our properties of logs, we say, oh, well, that really becomes division, right? So this is the same as 4 natural log of 3 over 6, which is the same as 4 natural log of a half. All right. Well, so we have 2 pi now of 3 natural log of 4, and then minus 4 natural log of a half. But again, using properties of logs, we can keep going. Why not? So this would become, the 3 goes in, natural log of 4 cubed, or if you like, well, Actually, let's do it this way. What's 4? It's 2 squared. And 2 squared, you can bring the 2 down, that's 6, natural log of 2. And then natural log of a half, whoops, why did I write minus there? It's plus 4 natural log of a half. This is the same as minus 4 natural log 2, because 1 over 2, no, natural log, if you flip it, put a minus. And so we end up with 6 log 2 minus 4 log 2 is 2 log 2 times 2 makes it 4 pi natural log of 2. And there you go. Now you might say, wait, could we, as a hypothetical, have stopped here? And the answer is, yeah. We're not testing you on can you simplify to what we think it would be the nicest looking form. We just care, can you get the answer? So if you stopped here, that's fine. It doesn't say simplify as much as possible. But of course, this looks prettier. And you know, math should be beautiful. You may not believe that all the time when you see some of these answers. 4 pi log 2 is beautiful? Yeah, I think so. It's a lovely answer. Beautiful answer. And all right, well, good. Whew, that one was a bit of a workout, but we made it, and let's keep going. Number 6, given the values of a function f at x equals 0, 1, 2, 3, 4 in the table below, so that's our table, estimate the integral 0 to 4 of f of x dx using the trapezoid rule with 4 strips of equal width. Okay, so we kind of have to remind ourselves, how does the trapezoid rule work? Now, I remember the trapezoid rule as this 1, 2, 2, 2, 1, which just means we're going to scale the first value by 1, the intermediate values by 2, and the last value by 1. But there's a small catch, which is that you also have to say, well, look, because we're scaling everything by 2, there will be this extra factor of a half. Okay, so let's go through, and of course, you know, what does this all mean? Well, it means the following. So we're going to have our interval is 0 to 4, and we're going to have 4 strips of equal width. Well, of course, if you chop 0 to 4 up into 4 pieces of equal width, not surprising, you end up at the points 0, 1, 2, 3, 4. It's like, you know, they gave us the table, so of course that's what we'll have. And so for us, we're in good shape because the width is 1. All right, so what do we have? Well, we're going to have the width, delta x, and then we're going to have that times a half, and then it's 1 times the first endpoint, 2 in the next point, 2 for the next one, 2 for the next one, and then we're at the other endpoint, so we're back to 1 again. So this is what I mean by the 1, 2, 2, 2, 2, 1. 1, 2, 2, 2, 2, 1. And the half is the half. That essentially is because you're sort of double counting most of the terms. Okay, so now what do we have here? Well, delta x is our 1. We have a half. Then we're going to have 1 times f of 0, which is 3. 2 times f of 1, which is 2. 2 times f of 2, which is 1. 2 times f of 3, which is 2 again. And 1 times f of 4, which is 1. All right, so this is a half of 3 plus 4 plus 2 plus 4 plus 1. Well, if you see here, that's 10. And add another 4 is 14. And a half times 14 makes 7. All right, now before you leave, make sure that that answer makes sense. Now, how do you say, well, how do I know if it makes sense? Well, think about this function. It's roughly around 2, right? Sometimes it's 3, sometimes it's 1, sometimes it's 2, but it's roughly around 2. So, you know, vaguely the height is 2-ish. The width is 4. So if I have something around 2-ish times 4, I should have something 8-ish. Well, 7 is 8-ish. It's close to 8. So that's a good sign. If we had gone 14, oops, we probably missed a factor, right? Maybe we forgot the half. Or maybe if we got like 7 halves, like, whoops, we overdid it. And so stop for a second and say, is this a reasonable answer? And oftentimes that'll save you some points. Like, oh wait, I'm off by something. Like, I feel I'm like twice as big as I should be, or I'm half as big as I should be. It doesn't hurt to ask, is my answer reasonable? In fact, I would say it more than doesn't hurt, it helps. All right, so now on to part B. So if f double prime is continuous and f double prime is less than or equal to 3 for all x in 0, 4, how many steps should we choose for the trapezoid rule if we want the error in estimating the integral from 0 to 4 of f of x dx to be at most 0.16? I say, oh, okay, well, how do we do that? Well, I say, hey, you know what? Our error is bounded by this expression. Now, let's dig into what our pieces are. So m here, they didn't tell us what that was, but this is our bound for f double prime. Now, what's the worst case scenario? They told us 3. B and A, we're so used to those. Those are our endpoints. And this is our number of, what do we call it here? Number of steps. Sometimes we might call it the number of divisions, how finely we're chopping. A larger value of n should give us a better approximation. And that's what this is saying. Also, you can think of m saying what? Well, hey, if your f double prime is small, then our function shouldn't change too much. And so it should be easier to approximate. But if f double prime is large, our function can change dramatically, so we should need more approximation. So, okay, so that lines up with our intuition. So our goal is to bound this error, make it small. So we say, oh, we can, instead of thinking of bounding this error, we'll really bound this expression. So we want m b minus a cubed over 12n squared to be bounded by 0.16. Now, 0.16, we can think of that as 16 over 100, right? And then you can say, oh, well, we could clean that up, for example. They're both divisible by 4. So this is the same as 4 over 25. Okay, so now let's fill in what we know. Because we know things. We know a lot of things. But in this case, what do we know? We know something about m. It's our bound for our second derivative, so this part right here is 3. And the b minus a, well, that's our 0 minus 4. So this is 4 minus 0. Okay, good. So, updating, we need the following. We need 3 times 4 cubed over 12 times n squared to be less than or equal to 4 over 25. Now, we can save ourselves some work by cleaning things up. Notice I have a 3 and I can pull off a 4, and that would give us a 12, so I can get a cancellation. So we can get 4 squared over n squared should be less than or equal to 4 over 25. Okay. Now, there's a couple things you can do here. What I would do is, okay, so let me tell you a couple things. You could flip both sides, but remember, if you flip both sides, you have to flip the inequalities. I'm going to cross multiply. So I'm going to move the n squared across, move that 25 across, and we could even divide by a 4, right? Notice how I have a 4 squared and a 4. I could just do that really quickly. So this becomes 100 needs to be less than or equal to n squared, or taking the square roots, we need that 10 needs to be less than or equal to n. All right, so that's our answer. What is this saying? It says that the number of steps, if it's at least 10, then this expression is at most 0.16, which means our error is at most 0.16. So 10 is enough. Now, could we choose 100? Yes, we could. But when it says how many steps, usually there's an implicit fewest involved. What's the fewest number of steps needed? And in our case, we could say, as soon as we hit 10 steps, we're guaranteed our error is at most 0.16. It's probably less than that, because this is a very generous error estimate, but that's okay. We just need to know, what's guaranteed. So at n equals 10, we're guaranteed. Life is good. Okay, great. And notice they give us the error estimates. So we don't have to memorize the formulas, but do make sure you know what things are. They didn't say explicitly what this m was. We had to get it from remembering things. But of course, in some sense, it's context. Say, oh, well, they gave us something about f double prime. That's probably m, right? Yeah, it is. So, when in doubt, if you don't remember everything, use context. Context clues go a long way. Okay, whew, almost done. One more, one last one to go. Our last problem, number 7. Evaluate the improper integral. Integral from -1 to infinity, x plus 1, e to the minus 2x dx. And it says, if you use l'hôpital, l'hôpital, mon ami, all right, indicate where you use the rule. Now it's an improper integral, so we should ask, why is it improper? Because there's two ways an integral can be improper, and sometimes you get both in the same integral. One way that it can be improper is if the integral has a vertical asymptote. In other words, there's like a division by 0 here. In this case, we're okay. There's no real division going on. Yeah, the exponential can be thought of as downstairs, but the exponential is never 0. The other way, of course, is horizontally, and that is what we have going on here with our infinity. All right, so we do have an improper integral. So this is truly an improper integral question, but that's all right. We know how to handle these, right? Where do we begin? Well, one thing we can do is we can say, well, let's not worry about the bounds, and say the following. Let's do it if there were no bounds. So you had x plus 1 e to the minus 2x dx. How would you integrate this? Well, here, this is something where this part, okay, so first off, I'm humming and hawing to say this is not on our list of our 10 basic integrals, but it's not far off. The x is throwing us off. We'd like to get rid of the x. And what's an easy way to get rid of an x? Well, if we differentiated it, it would go away. The e to the minus 2x, doesn't matter what you do to it, integrate, differentiate, it's still going to look like e to the minus 2x, maybe throw in a constant somewhere. So whenever you have exponential functions, great candidate for integration by parts. So we're going to do some integration by parts. We're going to let this part be our u, because we want that to go away, and it goes away with taking derivatives. And then the exponential function, great candidate for our dv. So then du becomes dx, and the integral of e to the minus 2x is minus a half e to the minus 2x. So this would become uv, so minus a half x plus 1 e to the minus 2x, and then minus the integral of v du. So minus a half e to the minus 2x dx. Okay, so this is minus a half x plus 1 e to the minus 2x. Minus minus makes a plus a half, but we're going to get another minus a half, right, because e to the minus 2x. So there's, all together, it becomes a minus a fourth e to the minus 2x. and plus c. All right, so there we go. That's our integral. Now we could do things such as putting things together, but for now I think we're okay. All right. So back to our problem, because this is the indefinite integral, but definitely this is a definite integral because we have bounds. And we can say, well, if we were being very careful here and wanted to look, we're not going to miss any points at all, we'd say technically this is our limit as our bound approaches infinity of the integral -1 to b of x plus 1 e to the minus 2x dx. You say, well, wait, we know how to integrate that. It's right there. So this is our limit as b goes to infinity of, well, we have our -1/2 x plus 1 e to the minus 2x minus 1/4 e to the minus 2x. Evaluate that from -1 to b. We don't need to put in the plus c, it goes away. Okay, and all right, so what do we have? This is our limit as b goes to infinity of -1/2 b plus 1 e to the minus 2b minus 1/4 e to the minus 2b. Subtract, and then here, plug in -1. Oh, -1 plus 1 is 0. That's convenient. And then we're going to have minus and 1/4 e to the minus 2 times -1 makes e squared. All right, good, good. Now, a couple of things. Minus minus makes a plus. This part is a constant, so this is going to go to 1/4 e squared. Exponential function, e to the minus 2b as b goes to infinity, goes to 0, because that's what the exponential function does. And then this part right here, we should think about. So this is b plus 1 over e to the 2b, because the negative exponent moves downstairs, which goes to infinity over infinity. So by L'Hopital, so I'm marking here, I'm using L'Hopital. This is the same as the limit as b goes to infinity of 1 over 2 e to the 2b. So I take 0 to the top, 0 to the bottom, which is 0. So this part also goes to 0. So it goes to 0, goes to 0, goes to 1/4 e squared. So our final answer is 1/4 e squared. And we're done. We're done, right? And we marked where we used L'Hopital, and so there we go. Life is good. And all right, well, that was a fun test. I hope you enjoyed it. I know I enjoyed it. And well, of course, there's always more tests, more practice, and good luck. I hope you do great. And see you again. Bye.